Hello and welcome to Calculus, and this video we're going to look at section 4-4, the fundamental theorem of calculus, the day you have been waiting for all year, the FTC. Really big section here. We got some bullets to cover. Evaluate a definite integral using this fundamental theorem of calculus. So all that summation stuff is in the past. We will understand and use the mean value theorem for integrals. We've seen mean value theorems before. Find the average value of a function on a closed interval. Understand and use the second fundamental theorem of calculus. Just one fundamental theorem is not enough. We got two. And then also understand and use the net change theorem. Okay, big day, exciting times. Let's jump in. So we've now been introduced to the two major branches of calculus: differential calculus, introduced with the tangent line problem, and integral calculus, introduced with the area problem. So far, these two problems have seemed unrelated, but there is a very close connection. The connection was discovered independently by Isaac Newton and Gottfried Leibniz, and is stated in the fundamental theorem of calculus. Informally, the theorem states that the differentiation and the definite integration are inverse operations, in the same sense that division and multiplication are inverse operations. To see how Newton and Leibniz might have anticipated this relationship, consider the approximation shown in the figure. I'll get to that in a second. Actually, I might as well just jump to it now. Here we go. So on the left here, we've got this box, and we've got a secant line going through the box. And if we go up this way, that is our change in the y value. And if we move across left to right, that is a change in the x value. So to find the slope of that secant line, we used change in y over change in x, delta y over delta x. So slope is about the same thing as delta y over delta x. And keep in mind, this is division. Now, definite integration, here we have a rectangle again, but we're not finding the slope of a line through it. We're finding the area of the rectangle. What is area? Base times height. Our base is our movement along the x-axis, change in x. Our height is our movement along the y-axis, delta y. So area is dy times dx, or multiplication. So just as dividing and multiplying are inverse operations, that still trickles through into calculus and makes their parent operations also inverses. Division leads to derivatives, multiplication leads to integration or area, so those two operations are also inverses. Blah, 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 blah. The slope of the tangent line was defined as a quotient. The slope of the secant line, similarly, the area of the region under the curve was the product of delta x times delta y. So at least in the primitive approximation stage, the operations of differentiation and definite integration appear to have an inverse relationship in the same sense that dividing and multiplying are inverses. The FTC states that the limit process used to define the derivative and definite integral preserve this inverse relationship. Okay. So here throughout this chapter, we've been using the integral sign to denote an antiderivative or a family of functions, and a definite integral as a number. So anti-deriving, we have our little squiggly here with f of x dx. Definite integration, there are numbers at the top and the bottom of that little squiggly. When you anti-derive, don't ever forget a plus c at the end of your answer. With definite integration, there is no plus c. This is not a family of functions. This is going to be a numerical value when we're all done. So the use of the same symbol for both operations makes it appear that they're related. In early work with calculus, however, it was not known that these two operations were related. The symbol there was first applied to the definite integral by Leibniz and was derived from the letter S. Leibniz calculated the area as an infinite sum, thus he used the letter S. So here in Theorem 411, of course my favorite in the whole class, the fundamental theorem of calculus. Let me make that a little bigger. There we go. If a function f is continuous on a closed interval from a to b, and capital F is an antiderivative of f on that interval, then the definite integral from a to b of f of x dx is capital F of b minus capital F of a. And down here in the box, we have the slick little guidelines to using the fundamental theorem. So provided that you can find an antiderivative of our function, you now have a way to evaluate a definite integral without using the limit of a sum. So when applying the FTC, the notation shown below is convenient. So here on the left is our squiggly from a to b of lowercase f of x dx. Now when we antiderive, I sort of mentally imagined that squiggly sort of sliding across the function, and it makes it into the antiderivative. Here we just denote that with the capital F of x. When the squiggly gets to the other side, it becomes this right bracket. Lower limit a is at the bottom of the bracket, b is at the top of the bracket. Now b, this is sort of like a diving board, and b's on top, so b jumps into the pool first. So that becomes this capital F of b. The fundamental theorem always has a minus in here, and then the lower limit gets its turn to jump into the pool, f of a. So we evaluate the upper limit in the antiderivative, giving us this value here, minus we put the lower limit through our antiderivative, getting this value, and then we just subtract. So here's just a real basic example. Antiderive, or definite integral, from 1 to 3 of x to the third dx. If we did this with the limit process, there'd be a lot of algebra involved, but we'd eventually get to the right answer. But now with the fundamental theorem of calculus, here we have our definite integral from 1 to 3 of x cubed dx. When the integration symbol moves across the function, we antiderive it. X to the fourth over 4. We raise the power by 1, divide by the new power. Our bracket appears with our upper and lower limits on. So now first this 3 jumps into this fraction. So we have 3 to the fourth divided by 4. And then we have our minus sign. And then the lower limit jumps in 1 to the fourth over 4. So we use those powers of exponents, get those to be numbers. We have 81 fourths minus 1 fourth, which is 80 fourths, or 20. Now here you might be thinking, okay, we antiderived. What about the constant of integration? So it's not necessary to include that constant because of this. So if we antiderive, we could put f of x plus c on there, and then our upper limit jumps in. So we have this f of b plus c. And then we have minus. Notice the grouping symbols. We're subtracting this as a group. Our lower limit a jumps in, and now it's f of a plus c. When we distribute this negative, now it's f of b minus f of a, and this positive c is now a minus c. So this negative c and this positive c are going to cancel each other out. There is no longer an unknown arbitrary constant. Insight. The FTC is a foundational concept tested throughout the AP exam by means of analytic, verbal, numerical, or graphical approaches. Of course, it's going to be on the test in multiple ways. It is the heart of calculus. Now I'm going to back up here in the slideshow. Let's revisit some examples that I tortured you with earlier in this chapter. Remember this example, number 6? I think this was in 4.2. We wanted to find the area of 4 minus x squared, bounded by the x-axis from 1 to 2. We found our delta x was 1 over n, and then here was our formula, 4 minus x squared, and this was our right endpoint formula. So let's think back to all the algebra here on this. Let's see, first we FOILed this out. We pulled the 1 over n out front. When we distributed the negative, we had a 4 minus 1. That became this 3 minus 2i minus I squared. We distributed the 1 over n and the summation symbols. We replaced stuff with our I formulas. We did all this work, and we finally arrived at the answer 5/3. Gee, it looks like this is going to be a little easier to do now. Here's our definite integral from 1 to 2. Here is our function, 4 minus x squared dx. So that definite integral sign is sort of going to slide across here, and we antiderive. So we're going to have a 4x minus x cubed over 3. And the antiderivative symbol, definite integral, when it got over here, it transforms into a bracket from 1 to 2. 2 is on the top of the diving board, so the 2 is going to jump in first. So we're going to have 4 times 2, that's an 8, minus 2 jumps in here. 2 cubed is 8 over 3, 8/3. Fundamental theorem is always a minus. Now we're going to evaluate our lower limit as a group, so I put a grouping symbol in there. The 1 jumps in, 4 times 1 is 4, minus the 1 jumps into the fraction here. 1 cubed over 3 is 1/3. Much easier than using our limit. Let's see here. I'm going to turn everything to thirds and distribute the negative. 8 is 24/3 minus this 8/3. We'll distribute a negative here. 4 is 12/3. Distribute here. That turns into a plus 1/3. So we have a common denominator of all of those is 3. 24 minus 8, that's 16. 16 minus 12 is 4. 4 plus 1 is 5. 5/3 by using our fundamental theorem of calc, and then again replaces all of this algebra, finding our endpoint formulas, all the the summation formulas getting substituted in. You know, that is all ancient history. We now have the fundamental theorem of calculus. And here's another blast from the past. Example 5 in the same section. X cubed between the x-axis and the vertical line 0 and 1. We did this with the limit definition. I don't have the algebra that we did there. But now with the fundamental theorem, we're going to antiderive x to the third. That's x to the fourth over 4. We move our antiderivative symbol over. It's now a bracket from 0 to 1. The 1 is on the top of the diving board, so it jumps in first. 1 to the fourth is 1 over 4. Now the lower limit zero's turn, it jumps in, minus 0 to the fourth over 4. So there our answer is just 1/4. Look how quick and easy that was. Something like that, with a little practice, you can do it in your head. Replaces all that summation stuff. Happy days. Okay, back to the examples. Here we go. Example 1, evaluate a definite integral. Evaluate these. Some nice slow pitches right across the plate. I'm just going to copy this one down. Antiderive from 1 to 2, x squared minus 3 dx. Remember, that just tells us what variable we are antideriving with respect to. So we antiderive this, x to the third over 3, raise the power by 1, divide by the new power. Negative 3 becomes a negative 3x. Our antiderivative or definite integral symbol is now over here as a bracket from 1 to 2. Upper limit's on top. It gets to jump into the pool first. So the 3 jumps in, and that, or the, excuse me, the 2 jumps in. That's going to be 2 cubed, or 8/3, minus 2 jumps in here. 2 times 3 is 6. Fundamental theorem says we subtract as a quantity. The lower limit jumps in. 1 cubed over 3 is a third. Minus 3 times 1 is 3. Okay, now I'm going to distribute the negative and write everything as thirds. 8/3 stays the same. See, 6 times 3 is 18, so that's 18/3. Distribute the negative, minus 1/3. Distribute here, that will be a plus. 3 is 9/3. And since the common denominator's there, we can just add and subtract our numerators. 8 minus 18 is negative 10. Negative 10 minus another one is negative 11. Negative 11 plus 9 leaves us at negative 2. That might be a good time to point out here, definite integrals can be negative. We are not finding the area under a curve because this is not going to stay completely in the quadrants 1 and 2 where we are positive, you know, above the x-axis. Let's see what's next here. Ooh, we got a radical. So definite integral from 1 to 4 of 3 root of x, I'm going to write as x to the 1/2 dx. Now we could move the 3 out, anti-derive, and then put the 3 back, or we could just keep the 3 there and let it come along for the ride. So let's see, this is 3x. We're going to have a 3x. Raise the power by 1. 1/2 plus 2/2 is 3/2. And we're going to divide by that same exponent, 3/2. And then we're going to move our definite integral sign is now over, turns into a bracket from 1 to 4. Now before we evaluate that, let's clean it up a little bit. I am going to bring the 3/2 up and flip it, so now it's a 2/3. So let's see, 2 over 3 times 3 over 1, that's going to be 6 over 3, or just turn into a 2, x to the 3/2. And I'm going to write it like this. X to the 3/2 means it's the square root of x cubed. Okay. Oop, and I forgot my bracket. From 1 to 4. Now we get to evaluate. Ooh, and let's do it like this so we can pull this off without a calculator. We got our 2, and then we're going to have a square root of x, but you know that cubed that's under the radical with the x through the properties of exponents, we could sort of move that cubed out of here and put it out here. It's not going to hurt anything. We'll still get the same answer, and it's going to be a little easier to evaluate. Okay, so upper limit jumps in first. So we're going to have a 2 times, when the 4 jumps in there, it's the square root of 4, and that's a 2. And then we take that to this third power. 2 to the third power is 8. And then we're going to minus, when we put our lower limit in, 2 times, the 1 jumps in. 1 square rooted is 1. 1 to the third is 1. So what do we got here? 2 times 8 is 16, minus 2, last I checked, that's 14. And there we go. Our definite integral from 1 to 4 of 3 times the root of x. Now now that I think about it, this we could consider area. Because the function that we were evaluating, 3 times the root of x, would stay up here in the first quadrant. And we went from 1 to 4. So we could look at B's answer as area under a curve. Okay, we are not having fun until we do a trig function. 0 to quarter pi secant squared of x dx. Okay, we got to anti-derive that, or think, what did we derive to get secant squared? Well, of course, that was tan x. And the integral sign is now over here on the right as a bracket from 0 to quarter pi. All right, upper limit gets its first turn, jumps in, tan at a quarter pi, minus lower limit jumps in, tan of 0. Okay, unit circle time, tan a quarter pi, well that's 1, minus the tan of 0, that's 0. 1 minus 0 is 1. All right, there we go. So just some very basic definite integrals using the fundamental theorem of calculus. Now these are pretty typical ones here. Here's one that's a little different because of the absolute value bars. These bars just throw a little monkey wrench in there because it's not your typical polynomial function. We got to think about the nature of this graph. Absolute value bar graphs are going to be V-shaped. Unless they're shifted up or down, this one's not. It is going to bounce off the x-axis somewhere. So let's find out where this one hits the x-axis. Hit x-axis, question mark. How do we do that? Well, when we hit the x-axis, our y value is 0. So we are going to set what is in the bars equal to 0. So x is going to equal, add 1, divide by 2. X is a half. So if we were looking at a graph of this, here's x is a half. We again know the graph is going to be V-shaped, so it's going to come in, it's going to hit a half, bounce off, and then head up this way. And we want to find the area from 0 to 2. And since we're bouncing off the x-axis at a half, we're going to find this area. And then, somewhere over here would be 2. We're going to find this area. So because the nature of this graph, we're going to have to break this definite integral up into two integrals. And I see up here in the corner the book might have a little better picture than me. Yeah, let's use this one. Make sure you do sketch this down in your notes, though, somewhere. And I guess we could even compute, we put a 0 in, this height would be a 1. And then if we put 2 in there, this height would be 3. So we could just do this by finding areas of triangles, half base times height, but that's no fun. We're not using calculus if we do it that way. There we go. So let's see. To the left of this intersection point, we have a negative sloped line. So we're going to have to set up one integral from 0 to a half. Now because, remember, if you look at the graph here, we're going downhill. This is negatively sloped. So when the bars turn everything positive, this is our negative option, negative quantity 2x minus 1 dx. So that will give us this area. I guess I'll just keep using black ink and color that in. Now I'll switch to red because we're not done finding area. We're going to need another integral. This one left off at a half. So we got to pick up at a half. And now we're going to go to the end at 2. So this I'm going to sort of represent here with the red ink. This is back where now we've bounced off the x-axis. Our graph is positively sloped going uphill. So that is what is in the bars left as a positive. 2x minus 1 dx. So we've got kind of twice the fun here. We're going to evaluate a couple of definite integrals. And I guess since I need this room, I can get rid of my picture now. Sort of just slide it out of the way. All right, and one more thing to sort of clean this up. I am going to distribute this negative. So we're going to have a definite integral from 0 to a half, negative 2x plus 1 dx. Plus, and I guess this one's just going to stay the same, 1 half to 2, 2x minus 1 dx. All right, it is time to use the fundamental theorem of fundamental theorem of calculus twice, and then we get to evaluate each of those using their distinct upper and lower limits. So here when we antiderive this one, we're going to get negative 2x squared divided by 2, and the 2's are going to cancel. So that's just going to be a negative x squared. Plus 1 will antiderive to x. And this definite integral is going to be evaluated from 0 to a half. Plus, let me go back to red ink. Let's see here. I should have left myself a little more, a little more room, like so. So now when we antiderive this, it's going to be 2x squared over 2, or positive x squared, minus 1x, and this gets evaluated from a half to 2. Now, over the years of teaching this, many students, if they're going to make a mistake, it's going to happen right here, and it's not even going to be calculus or even algebraic. It's just going to be arithmetic and losing track of a negative or not grouping something that should be grouped. So let's see here. First, we've got a negative x squared plus x, and then the half is going to jump in. Notice that negative is outside the brackets. That will not get squared away. So we've got a half in there, and we've got a half there. Now we're going to minus, as a quantity, 0 jumps in, so that's just going to be 0 squared plus 0. 0 plus 0. It's real easy to fall into the habit when you see the lower limit of 0 to just think it's going to 0 out. Be extra careful if you're evaluating a quantity like x minus 1 quantity squared. When you put a 0 in here, you are going to get a 1 as your output. So don't just write off a lower limit of 0, but just to save room in this, I am going to erase it here on my board. Now let's jump over to the stuff in red. So we're adding here, remember this is the area of the small triangle, Now we're going to add in the area of a bigger triangle. So the 2 jumps in first. We're going to have a 2 squared, that's 4. Minus 2 jumps in for this x, that's just a 2. And now we are going to subtract as a quantity. The 1/2 is going to jump in. 1/2, and that's going to be squared. Squared. Minus 1/2 jumps in for that x, so it's minus 1/2. Again, real easy to lose track of a negative or not have grouping symbols when necessary. That's going to blow up your final answer. So just some arithmetic. 1/2 squared is a fourth, and it's negative. Negative a fourth. Plus a half. Plus 4 minus 2, that's 2. And now we are going to subtract. Here I'm going to distribute this negative. So distribute there, that's going to be a half squared or a fourth, minus a fourth. And then this minus is going to jump in and change that into a plus 1/2. Okay, before I worry about a common denominator, let's see if anything cancels here. Negative a quarter, and another negative a quarter is negative a half. So those will cancel one of these positive halves. And then we're left with 2 plus a half, which is 2.5. Or if you like impropers, that would be 5 halves. All right, let's see what's coming up next. Example 3, fundamental theorem to find area. So this is definitely going to be above the x-axis. Find the area of the region bounded by the graph of 1 over x. So let me draw a quick 1 over x graph here. They look a little something like this. And we want to find the area bounded by the x-axis and the vertical lines from 1 to e. Now e might seem like an odd upper limit, but you'll see why in a minute. So here's 1, and then e is about 2.72. I'm going to put that about out here. So what we're looking for is area under the curve. And because they've chosen these very specific limits, 1 to e, this will be easy to tackle even without a calculator. So let's set this up. You know, here in the description, they've given us just the description, not the official calculus setup. So we are going to antiderive and definite integral evaluate from 1 to e of the function 1 over x dx. Okay, so let's antiderive that. What is the antiderivative of 1 over x? Well, that's natural log of x, natural log x. I'm not going to put the bars around it because 1 and e, our limits are both positive, so we don't have to worry about that. Bracket over here, 1 to e. So sitting up top of that bracket is e. It gets to dive into the pool first. E jumps in. We get the natural log of e. Fundamental theorem says subtract natural log of lower limit 1. Okay, the natural log of e, remember ln's and e's are inverses, and that is an e to the first. So when the natural log and e cancel, that answer is just a 1. Minus, and what is the natural log of 1? Well, that's 0. 1 is where natural log crosses the x-axis, so its value is 0. 1 minus 0 is exactly 1. So that area under the curve 1 over x from 1 to e is exactly equal to 1. Very nice. And there's what it would look like on a TI-89. And our TI-89s do have the feature under the calculus menu. You'll see one of the options is antiderive, and they will give you a left bracket. And we could type in our function, 1 divided by x, comma. Now we need to tell it what variable to do antiderive with. Even though there's only one variable here, the calculator will not do anything unless we tell it. So we tell it to antiderive with respect to x, and we give it another comma, and we put in 1, our lower limit, and then another comma, and then our upper limit. In this case, it was e, upper. And then we close off the parenthesis that they gave us after the squiggly. And then the calculator would just spit out a 1, and you have your answer. Okay, mean value theorem for integrals. We've seen mean value theorems before for derivatives, so naturally the inverse operation will also have some form of a mean value. Back in section 4.2, we saw the area of a region under a curve is greater than the area of a region of an inscribed rectangle and less than the area of a circumscribed rectangle. Remember our upper or our over and under estimates. The mean value theorem for integrals states somewhere that between the inscribed and the circumscribed, there is one perfect rectangle whose area is precisely equal to the area of the region under the curve. So again, here, this area under the curve here, we could break that up into some number of rectangles and come up with a pretty good estimate, either over or under. The mean value theorem says there is one perfect rectangle, that this rectangle that I'm tracing around in blue has the exact same area in the rectangle as is under this curve. So notice there's a little bit of area here that's in the rectangle, not in the curve, but that is perfectly balanced by this area that is under the curve, but not in the rectangle. So again, this area under the curve is perfectly in this rectangle. One rectangle with the exact same area as the area under the curve. And notice here this notation, the mean value, I think, is this the same over here? Yeah, f of c times b minus a. Well, remember, the area of a rectangle is just base times height. Here's the base of the rectangle. What's that length? B minus a. What's the height of this rectangle? Well, there's some value c that when we put it into the function, it gives us the height of that one perfect rectangle. So that's our height, f of c. F of c. So here is the area of the rectangle, base times height, and here it is represented as a definite integral from a to b of f of x dx. So what we're finding here, sometimes we can find this c value that gives us that perfect height. Okay. And that leads to average value of a function. Now here's how they're related. Oops, back up, back. On here, oops, I went in the wrong direction. There it is. So the mean value, we want to find this one perfect rectangle using, or sometimes we want to find this c value that makes it happen. Well, we'll also be able to see what is that height on the y-axis. What is the height of that one perfect rectangle that has the same area as the area under the curve? That is the average value of the function. The average value of a function is some number on the y-axis. So that value f of c that's given in the mean value theorem for integrals is called the average value of our function on that interval from a to b. The definition here in the box of that average value, it's pretty basic. We take our definite integral here, but we put a fraction out front. The fraction is 1 over b minus a. You know, that is the fraction that will reduce this area down to that average value. So this definition says if f is integrable on a closed interval from a to b, then the average value of that function on that interval is 1 over b minus a times our definite integral. So here again, graphical representation. This area in the rectangle is exactly the same as the area under this curve. The average value is that height on the y-axis. The average value is a number on the y-axis. It is the height of the one perfect rectangle that has the same area as the area under the curve. And let's see that there's an example that goes along with this. Oh, there it is. Find the average value of this function on the interval from 1 to 4. So 3x squared minus 2x, it is parabolic in shape opening up. Here's the book's graph on that. We want to find the area from 1 to 4 here and turn that into an average value. Ooh, and I spoiled the surprise. Don't look at that. Okay. So let's set this up. Average value. Just because it's new to us, I'm going to write it here. That's the 1 over b minus a. Definite integral from a to b of f of x dx. So let's start plugging in the stuff specific to our problem. 1 over b is 4 minus a is 1, 1/4. or excuse me, 1 over 4 minus 1. And then we have our definite integral symbol, lower limit 1, upper limit 4. And then we put in our function here 3x squared minus 2x, and then dx, because we're going to antiderive with respect to the x-axis. All right. So 1 over 4 minus 1, that's 1/3. And I'm going to put a grouping symbol here, because remember this antiderivative symbol is going to work its way across. Over here, it's going to turn into a bracket. But first, we're going to antiderive on the way. This is going to become 3x to the third over 3. So the 3's will cancel. So that's just x cubed. Minus, this will become 2x squared over 2. And the 2's will cancel. Oh, so that's just x squared. That's nice. And we're going to evaluate that from 1 to 4. Now be extra careful. You know we've got this 1/3 out here, and that's going to be distributed to everything. So here's 1/3. I'll do that in red ink, and way over here I'll put another bracket in red because that 1/3 will be distributed to everything. And now I'm going to switch to blue for my fundamental theorem of calculus. Upper limit jumps in first. That's going to be 4 to the third power minus lower limit 1 jumps in, 1 squared goes here. And then I'm going to switch ink yet again. Oh no, I guess that's it. Yeah, we did upper and lower limits. I guess I didn't need to put that bracket so far. Whoa, over there. Okay. So we've got our 1/3. 4 to the third is 64. And then minus 1 squared is 1. So oh, hold on. Back. I did mess up. What the heck am I doing? Look at that. I forgot the 4 squared, didn't I? You were probably yelling at your screen. What are you doing, Kaiser? I caught it quick enough, though. At least I won't have to go back and redo the whole example. So we get our 4 to the third, and then the 4 jumps in here, 4 squared. And then we do minus. Now we're doing our lower limit. Now the 1 jumps in. That's going to be 1 to the third minus this 1 jumps in, 1 squared. Aha, so I did need my bracket way over there. Okay. Disaster averted. Okay, now 1/3. 4 to the third, that is 64, minus 4 squared is 16. And then we're going to have, this is 1 cubed is 1, minus 1 squared is 1, 1 minus 1 is 0. So that becomes minus a 0 minus 0, or just 0, so that's gone. So we have 1/3. 64 minus 16 is 48. And 1/3 times 48, or 48 divided by 3, is 16. So that is our average value. Remember now, this is not the area under the curve. The area under the curve would be this if we ignore this 1/3. Area under the curve is 48 square units. But when we bring in that 1/3, that gives us our height on the y-axis. So again, this area here is 48 square units. But the height on the y-axis, our average value, is 16. And if you look at the base here, b minus a, 4 minus 1 is 3, 4 times 16, base times height, that is the area there, 16. Okay, let's see here. We're going to go through this example 5. It is not in your notes. It's just a real kind of life application to the fundamental theorem of calculus. And then it's probably a good spot to end this video, and we'll finish 4.4 in another video. But here's a neat application of a fundamental theorem type use in science. The speed of sound. At different altitudes in the Earth's atmosphere, speed of sound travels at different, or the speed of sound is different. Closer to the Earth, you have thicker atmosphere. It slows down sound. As you head up through the atmosphere thins, and you have spots where it will travel quicker. So the speed of sound in meters per second is modeled by this piecewise function. All the numbers are in kilometers above Earth. So if you are on Earth up to 11.5 kilometers, this linear model works for the speed of sound. Between 11.5 and 22 kilometers of altitude, it is a constant 295. From 22 to 32 clicks up, it is linear again with this linear function. From 32 to 50, it is a different linear function. And from 50 to 80 kilometers up, we have this other linear function. Notice that's one with the negative slope there. Interesting. When you graph all those linear pieces, it looks like this. So the question is posed, what is the average speed of sound over that interval? So what we're looking for here is one perfect rectangle that would have the same area as the area under the curve. So here's some area above, here's some area above. That should cancel the area below. It looks like I'm off. It'd probably be more down here. And how would you do that with calculus? Well, you'd set up a bunch of different integrals, one for each piece of the piecewise function. So here's one from 0 to 11.5 clicks of the linear function. Anti-derive and evaluate, you get this value. The next interval was 11.5 to 22, different function, anti-derive and evaluate. You do that for each of those different layers in the atmosphere, so to speak. If we add up all of those numbers, we get our integral all the way from 0, Earth's surface, up to 80 kilometers up. We get 24,640. And then if we take the average value of that, 1/80th of that integral, we get about 308 meters per second. Okay, again, not something we're going to do in class. It would take way too long, but I still wanted to show it to you, let you know that it is out there. This is a good place to stop this video. The next video picks up with the second fundamental theorem of calculus. And let me just take a quick 6, 7, 8, 9, 10. Yeah, we'll have some good stuff to do in there. So I will see you in the next video.